So this is lecture 42. It was originally on tangible incompleteness. Now it's lectures on embedded maximality by Harvey Friedman. Please.
Thank you. Okay, so I promised, and I'm going to deliver, that I actually finished the section on further investigations for chapter 3. And we're going to do that. Uh, this is the constant organization of the entire book. Uh, Chapter 3 is that reversals have been constant. I'm going to have to do a little change in the reversals just to make sure the notation matches what we've got now, but that's minor. And chapter 5, we're going to make a good start. I think I now know what chapter 5 is going to really be. I've got a fair amount of it organized. Uh, Not all the proofs though, but this we haven't talked about. This is important. This is going to be good too. And this has to be revisited to make this more mathematical and unified. See, we have this notion of embedding, and we're using it throughout. Uh, Embedded maximality. Here's just embeddings of the real point sets. So things are coming together strongly. All right. So with embedded maximality, we really have nothing new except I'll just point out uh, uh, whether I did anything much uh, so far. Nothing is new. Uh, yeah, okay. And then I don't think I did any. Yeah, I didn't. This is in pretty optimal form. Beyond finite usability, this is all the same from last time. Order theoretic usability is broader and but still implicitly pi 0, 1. Okay. And this is all pretty much the same with not many corrections. That's the core of this, the proofs that use large cardinals or omega 1 or Aleph omegas or roughly Zermelo is the core of this chapter where I do the actual proofs. Um, okay, and then I think I talked about this last time. You can do this with graphs and emulators. This is the one for I use for gifted high school for a very basic case. And graphs, simple graphs, we talked about that. That really is not any, the graphs, clicks through graphs are the same as change through relations. Um, and they're almost the same. Um, and that matches well. Emulators is a little different. There's a discrepancy of one dimension in here, that has to, and it's not totally straightforward to show that actually globally is the same. In other words, emulator usability is actually the same as graphs usability is the same as usability. Uh, and so from these, you get a reversal to con SRP. Now, further investigations is what I want to talk about today. All right, we discussed a number of investigations that lie beyond the scope of this book. We list a number of conjectures and questions. To begin with, we conjecture sharper reversals of IEU graph, IEU emulator than those given in the previous chapter section. So the sharper ones are this. These are all provably equivalent to WKL naught plus con SRP over RCA naught. And the only new idea here is that all these statements, what I'm saying is all these statements imply WKL naught over RCA naught. They imply WKL naught over RCA naught. And I'm not going to try to prove this. I don't want any mission creep. The expectation is that the chapter 4 reversal can be conducted in RCA naught from the beginning far enough to get a countable model with enough basic properties from which weak Koenig lemma naught can be derived by standard methods. I should say countable models because it has to be parameterized. Otherwise, you can't do this. Okay, so um, yes. Now, I guess I want to worry about this a little bit because actually, I don't quite believe this. I think this has to be modified because it seems like recursive WKL naught, every recursive infinite binary, infinite two tree has an infinite path. Recursive WKL naught might be enough to prove, is that enough to prove, uh, interesting, is it? I think that may be enough to prove with con SRP, enough to prove IEU. Yeah, I don't think a pi 0 1 sentence could possibly prove WKL naught. Well, it's a pi 0 1 sentence. It's not exactly a pi 0 1 sentence. It's probably equivalent to one over WKL naught, but still can't possibly prove WK. Yeah, so I think this is wrong, but it can be replaced by a more technical conjecture. I think maybe IEU emulator is probably equivalent to effective WKL naught plus con SRP. Maybe that is the theorem. I have to think about this. Um, yeah, and then maybe the remarks are still the same, that you get a countable model or whatever. Yeah, so this needs to be modified. It may be some remark that it can't possibly prove all of WKL naught. All right, so I'm going to have to fix this up some. All right, now recall the main thrust of embedded maximality is the determination of the usable functions. We envision this as being investigated in four large stages. Now, why did I say? Okay, four. Yeah, because I wanted four. Uh, I'll just clump this in more general F. Yeah. Okay. So in three, since the FR by convention partial functions from -1, 1 into -1, 1, this means the graph of F is a Boolean combination of polynomial inequalities over the rationals, just what you might expect. Yeah. So in the chapter, I only handled very basic F. In other words, in IEU, namely, you're looking at an interval that starts at 0. You're looking at the identity function on an interval that has left endpoint 0 closed, left closed, and then you're adding on a finite part. I mean, it's extremely low level, and we get all this large cardinals out of it from chapter 4. Uh, but order theoretic is an extremely natural collection. In fact, I even have a section on order theoretic in the book, in the chapter on order theoretic, because I wanted to use order theoretic to say that everything in sight is implicitly pi 0 1. So the usability of order theoretic functions is implicitly pi 0 1. That's why I did that. So, but now actually reworking everything, figuring out what the usable functions are for order theoretic F is a big deal. And I was thinking that I was making huge progress on this, but I decided this was beyond the scope of the book. I didn't really want to do that now. So that's a very doable project, I believe. It might be I don't know quite how hard it is, but I know it's not trivial for sure. I think it's tricky. So anyways, that's one thing. And then another class is the rational piecewise linear functions, yet more complicated with more issues, which ones of those are usable. And then rational semi-algebraic F in the sense that I mentioned. Then more general F, you know, I don't know exactly what that subject will look like, really. Um, One thing I'm missing in this chapter is some basic negative results. I don't know how I have some negative, there's a even as you know, there's a finite function that's strictly increasing that's not usable that comes up in the fundamental thin use theorem. But I don't have I haven't worked out any more profound or general kinds of negative results that certain functions aren't usable. So that's kind of missing. I might want to beef up some open questions there too. I'm not sure. All right. Um, so here's the usability conjectures. Let W be the set of all statements F is usable, where F is order theoretic. The set of true sentences in this class is low-level computable. That is, you can really figure out which ones are correct and which ones aren't. That every element of this class is either provable in SRP or refutable in RCA naught. See? The ones we care about involving IEU and so forth, those functions, they're definitely order theoretic, but also the usability is provable in SRP. All right, the elements of W are pre-well ordered under provable implication over WKL naught. And the ordinal is at most omega to the omega. Yeah, I feel like there's some that the ordering is not just simply a type omega. I don't think. All right, the relation in 3 is low-level computable. Provable implication is low-level computable. Every element of W is provably equivalent to WKL naught plus the consistency. So this is the thing that's wrong. I have to be careful about this. I think it's effective, some sort of effective WKL naught zero plus the consistency of a formal system, like standard formal systems. Yeah, another ones. All right, and then the same conjectures when you have K usability for various K, and then the same thing for rational piecewise linear and rational semi-algebraic. Same conjectures. And then there's the general usability question, which I think is worth mentioning. Is the set of all usable F, so these F may be infinite, is the set of all usable F complete analytic in the usual sense of descriptive set theory? Or is it Borel? Okay, now even the OTH usability conjecture 1 probably needs to proceed incrementally according to the structure of the given order theoretic function. Even the usability of the functions G union identity on J, where G is finite, seem to present difficulties. Yes. And yeah, I'll probably give some examples of such a thing where it seems a little tricky to figure out whether it's usable. Now, the dimension reduction raises the following question. Are there K usable F that are not K plus 1 usable? Almost certainly true, but I haven't, you have to do something. If so, can F be order theoretic or rational piecewise linear or rational semi-algebraic? We've seen in section 320 that usability and K usability are the same as usability graph, K usability graph. However, we have only a strong relationship between usability and K usability between usability, comma, K usability, and yeah, I don't mean between these two. A usability emulator, K usability emulator. Yeah, so the relationship to usability and emulator is not clear because I lose a dimension. If you go back to what I did, I think I talked about it last time. Uh, all right, so the emulator usability investigation, clarify the relationship between usability emulator and K usability emulator and usability K usability. Address all the above conjectures and questions for emulators. All right, for joint usability, so this is a topic I didn't want to put in the book where I had to put proofs in, but I put it here uh, and talk about an obvious proof without giving it. All right, so let K be a set of functions of the kind we're considering, and let S be a subset of minus 1, 1 to the K. We say that it's K embedded if and only if for all F and K, for every function in K, S is F embedded. Right, so it's just joint. So I'm treating all the elements of K as joint usability, that every one of them is usable. Now let K be a set of such functions. K is usable if and only if every ordered relation on every minus 1, 1 K has a K embedded maximal chain. All right, there's a level in there, I think. Yeah, okay. All right. Recall that the major goal of embedded maximality is to determine the usable F. In joint embedded maximality, the major goal is to determine the usable capital K. In other words, which finite sets of functions are usable. All of the issues raised so far and more need to be upgraded from embedded maximality to joint embedded maximality. So we can take almost any of the conjectures we're considering about embedded maximality and just put it onto joint embedded maximality for more research. In particular, finite embedded maximality is basically a subject completely finished by my section 3.5 with thin use. We believe that it can be reworked completely for finite joint embedded maximality, where K is a finite set of finite F. Okay, so who's that? Yeah. We believe there's a great deal to gain by developing joint embedded maximality. Specifically, we now present a clear extension of IEU whose proof is basically the same as that given in section 318 and 319.2, going back to section 312. That's the standard, that's the proofs of the standards of IEU. The simplest way to present this joint invariant extensions is as follows. JIEU is joint identity extension usability. If K is a finite set of strictly increasing finite functions, then F union the identity below the F union the identity below the minimum field element of F. So here's F. Here's how you get below F. I want all that filled up with the identity. All right, so that's what they took to prove this, and I probably would might need the same thing. That JIEU is provably equivalent to con SRP over WKL naught is what we have. Uh, okay, so the JIEU conjectures uh, just say that basically that jumping to a joint from single function doesn't really buy you any difference in strength. That's basically what this is saying. All right. So for WIEU, we have the same situation, the same conjectures at a lower level. All right, so that's enough with chapter three. Chapter three is pretty stable. I should, this weekend, I'm planning to have gone over it enough to put it on my website. So that means we have 3 and 4 on my website. Uh, so now we're moving to 5. There's also a version of two on my website also. All right, so yeah, so that's just the book again. Okay, so here's chapter 5. So I defined this thing called the clique algorithm, which is a way of building a clique. Um, doesn't always have to be a maximal clique, but it has maximality properties. All right, we'll explain this. All right, so there's a way of building a clique where you start off with there's a deterministic way of building a clique that's kind of maximal. It doesn't have to literally be maximal, as we will see. Then there's a non-deterministic way of building a clique, just by getting by a small by a simplification, in fact, actually. And what we want to do here is we want to do some computational complexity and recursion theoretic study of what you get here. And I think that's pretty interesting. Uh, Now, global properties of when you put infinity here, so we're allowed. This means the length of the how long this algorithm runs. But you're allowed to, if you put infinity over here, you're talking about running it for infinitely long. So you get an infinite sequence at the end, not just a sequence of length r, but you get an infinite sequence at the end. And the question is, what is the description set theoretic uh, properties of that? I'll be going into that, next time probably. Uh, okay, and the non-deterministic case, uh, there are various questions you can ask uh, that make sense, descriptive set theoretically, about this situation. But then now we do something very far-reaching right here. Namely, we introduce an F. Remember, F is my standard letter I use, F, G, and H for in this book for partial maps from zero, from -1, 1 to -1, 1, close. In other words, these are one-dimensional maps. All right, now, and of course, we focused on when is F usable or not, right? Okay, so here's how F is embedded in these simple algorithms. You start with X naught, which is a k-tuple, and from -1, 1. You start with X naught, and then well, I'm going to describe this a little bit later, but the point is you incorporate F into the algorithm, okay? And now we define what we mean by F is usable as far as NDA. NDC means non-deterministic continuations, and K usable non-deterministic continuations. We talk about usability there. And then we want to prove a theorem, which I think is false. It has to be changed a little bit, not much. F is K usable. First of all, implication. F is K usable, then F is K usable in the algorithmic sense. Okay, so that's one direction, and then we want the other direction. So we get that F is K usable, and if and only if F is, wait a minute. Yeah, we want this. This is the equivalence we're already looking for. The old usability notion and the new algorithmic notion. Okay, so what happens is there's a weak kind of K usability that comes up here. And that's when the domain is not -1, 1, as it is with K usability. The domain is not -1, 1. The domain is going to be any structure, excuse me, any substructure of -1, 1 to the K. Well, I think it's one-dimensional. Yeah, any one-dimensional subset of -1, 1. Yeah, so we have the theorem that if you're K usable in this algorithmic sense, then F is weak K usable. In other words, the algorithmic form implies the original form. And then finally, this weak kind of usability implies regular usability. Okay. Now, I had written out a complete proof of this in a different context, this one here, so it's not too hair-raising. All right. Yeah. Okay. So the highlight is that IEU in this algorithmic form is also equivalent to a con SRP. I don't know what further investigations look like in the context of chapter 5. Okay, so let's talk about this clique algorithms, how that works. What does it look like? Okay, in the first section of this section 5.2, i.e. 5.2.1, we introduced two kinds of continuations. So we're trying to build long cliques. We're trying to build long cliques with some properties. So if at any stage you have a clique, then at the next stage you're going to have a longer clique. Okay. Now with the deterministic one, it's clear that you can just do this. It's just an algorithm. Uh, so in the deterministic case, what we use is positionally early. Actually, we should have meant. I think I need to say computer positionally earliest. Yeah, it's unique. We do that. You take the positionally earliest k-tuple of the concatenate. It's a subsequence of the concatenation, such that if you tack it on, you still have a clique. So you have a clique, and a continuation is a new vertex or element of -1, 1 to the k, new vertex that you can add on, maybe probably in the same spot in the boat, and help them out there. You can put this stranger in there. Okay, so the first kind is deterministic, and namely that we always use the positionally earliest subsequence to continue. And the second one is non-deterministic. The simplest second one is just ND clique. We just set it up so that we know that we just pick one. We don't necessarily pick this special one. So for the deterministic case, we actually take the what's called the earliest continuation. Now, roughly speaking, the earliest continuation is the continuation such that the placement is lexicographically least, where the lexicographic nature is reversed. In other words, reverse lexicographic order first. That'll work. All right. All right. For the non-deterministic case, um, when we bring in F, then we get something that's we're gonna run right into incompleteness from ZFC this way. All right. Okay, so formally, continuations. Cliques are normally defined as sets of vectors, but you can also treat them as sequences of vertices with any two distinct terms being adjacent as a clique. All right. Just the continuations just mean that we introduce a maybe I should say a continuation is any Yeah. Um, yes, for the deterministic one, the problem I have here is that what I didn't consider, yeah, it's not necessarily for the deterministic one, the problem is what happens when I get new numbers, when I'm supposed to get, when I run out of stuff. I didn't think this through. I didn't think through carefully enough what the deterministic case really amounts to here. Uh, yeah, that's an issue. How do I want to say this? Yeah. Um, the non-deterministic one with the functions f incorporated seem to be just fine. Um, yeah, I think I need to say this differently. We're building a clique. We have the notion of continuation, but in the non-deterministic case, we don't have to take the best continuation, the least continuation. We can instead do another continuation, which is pick something that is non-adjacent to the continuation. And I'm now beginning to think that there isn't a very natural deterministic thing here at all, now that I think about it. I'm not sure that it's worth doing. It may be that one should just go directly to into the important case. So how does this algorithm work? You have a graph G, order invariant graph G on -1, 1 to the k. You also have an initial vector x naught, which is a k-tuple. And what you do at any stage is you take what I call an early continuation. So we defined down here, there's the earliest, but there's I don't I guess the idea of using the earliest, which means that I'm doing something deterministic, doesn't make any sense. Because there's other parts that have to be non-deterministic for this to get interesting. So I think I'm going to remove some material about deterministic. Uh, but what you're allowed to do at any stage is so xi can be any tuple that is non-adjacent to a earliest continuation. xi is not adjacent to some continuation of x naught through xi minus 1. That's what I want to say. And the fact that that algorithm could obviously continue forever, because all you can do if you want is just recycle the continuations. But you're given the opportunity to replace a continuation by a vector that is a tuple that's not adjacent to it. Right. Now, so what? But now here's the point. The point is when I incorporate F, I'm signaling that I'm supposed to write down um, something. I'm supposed to write down something that's not adjacent to a continuation, as I said. But then the next term after is supposed to be f of that. So once I choose non-deterministically something that is not adjacent to an earliest continuation. So then I have to also write down immediately thereafter. Uh, I have to apply f to it. Okay, so it's incorporating f. And the thing that's independent is that for very basic f, you can't prove the statement that you can, in fact, continue this uh, indefinitely turns out to be independent of ZFC. It turns out to be equivalent to con SRP. Uh, yeah, so I didn't have a time to actually polish this up too clearly, but that's the idea. Uh, Now, the idea is that if I actually take an F, and by the way, if I do this with the F, in order for this statement to really follow from usability, in other words, F is usable should imply that I can use F in this non-deterministic algorithm and get that the non-deterministic algorithm can be performed performed along infinitely many steps or any finite number of steps, because by compactness, these are equivalent. So this is easily proved by starting with an F-embedded maximal chain and using that in order to navigate this construction. So it is a genuine finite form of the infinite statement, which is equivalent to one con of SRP, which actually is all of its examples are provable in WKL naught, yeah, and WKL naught. All right. Yeah, now to reverse it, so that's the proof of it. Um, you just continue the construction using the fact that this is an embedded maximal chain. It's really quite pretty and straightforward, but the reversal has to be considered. Now, the fact that I'm always recycling the earliest thing means that I'm somehow going to, at the end of this process, when we take the compact limit, so to speak, I'm going to be recycling everything. And so then I'm going to get, well, I don't quite get an invariant, an embedded maximal chain, a maximal clique. I get something weaker. It's not going to be maximal. It's going to be maximal only relatively to all tuples drawn uh, from a countable set. And then, so that leads to having to define a weak form of IEU. A weak form of IEU, uh, not requiring the density of the underlying space. And that's something I have known how to reverse in a different context. I got to look it up in my files because I already did it. Uh, I've got this in my files and I have to dig it out. So this that's how the reversal goes. The reversal is immediate in principle, but the problem is that you only get a weak form of maximality out of it. So you have to prove that you can get the strong form out of the weak form. So that's what this, uh, let's see if I can find it. Um, where's my table of contents? Yeah. Okay. So I'm convinced that I have the right chapter 5. I didn't actually execute it that well. I'm not sure there's a deterministic algorithm that's so important here. Uh, yeah, because I'm not getting new numbers, yeah. Yeah. So that's not it's not it doesn't look like that's a good way to go. I think I need to define the non-deterministic algorithm without the F first. Point out trivially that you can run it deterministically and it loops on itself. You don't even get arbitrarily large uh, denominators going or anything like that. Uh, yeah, so I think that this is really the best way of all to do this, to directly go to an algorithm. So if you just do the non-deterministic algorithm, uh, that doesn't really amount to any obvious interesting statement, but it is the right, conceptually, it's the right idea. But then you want to incorporate F into the fabric of this algorithm. So the idea is that on the on every other stage, half them, you will be applying F to the previous term. So you start with X naught, and you may come up with some X1, but then the next term is going to be F of X1. But actually, yeah, right. So we're kind of building a maximal chain, and we're also incorporating F into the maximal chain. And so you can see how this is going to be, if the algorithm can be run infinitely for any finite number of steps or infinitely many steps, same thing by compactness. Uh, if you can run it forever, for example, in the most extreme case, forever, then you know that you're going to be building a kind of maximal clique. But it won't be maximal with respect to every tuple from the whole interval minus 1, 1. It may be only from some sparse uh, count, some sparse infinite subset of 0 of minus 1, 1. And then you have to prove that you can reverse that. You have to show you can reverse that, which I've done in a different context. All right. So I think that I can stop now, I think. Yeah, yeah. Okay. So I hope that gave you a good idea. Everything will be much clearer next week on chapter 5. And chapter 5 is not nearly as big a deal as chapter 3. Okay, thank you. I'm done now.